So our second skill in our fifth learning unit here on chemistry of gases has to do with manipulating PV equals nRT to think about two important gas parameters, which are density of gas and molecular weight. So I'm going to show you just very briefly how we get to those two new equations. You're not going to need to worry about deriving them or anything. They'll be provided for you. Again, just something you're going to need to know how to use. We're also going to talk about this concept of partial pressure, which has to do with the fact that if we have a mixture of gases, each gas is going to contribute a portion or a partial amount of the total pressure that we see in that sample. So when we think about other ways to use PV equals nRT, don't worry when you see some new equations here that look scary. We're going to walk through them. Again, just understand they will be provided for you. You just want to know how to use them. So by identifying other relationships between variables that we have, we can actually expand on PV equals nRT to have two additional important parameters that are important to think about properties of gases, which are density and molecular weight. So let's take molecular weight or molar mass first, right? We know that molar mass is a relationship between the mass in grams and moles, right? We've known that. That's how we walk between mass and moles is molecular weight. So to figure out the number of moles we'd have, you actually take the grams and you divide by the molar mass. That will give you the number of moles. So what we're going to do here is we're going to substitute into our PV equals nRT grams for mass divided by molecular weight. So you'll notice here, this looks like an M. Anytime you see M in a chemical formula, not a chemical formula like magnesium chloride or something, but an M, a lowercase m in a chemical equation that we have here, that represents mass, and it will be mass in grams. If you see the letter N, that represents quantity of something, but in moles. Okay, so M is the mass of that substance in grams, and we can substitute N in here for mass in grams divided by molecular weight. So this is really just PV equals nRT, but now we're putting the mass of the gas in and its molecular weight. All this really does is give us an additional set of problems we could solve, where now we've got 1, 2, 3, 4, 5 variables that maybe if we gather the mass of gas that we have and know its pressure, volume, and temperature, we could figure out what that gas is because we can figure out its molecular weight. So kind of some neat problems we'll be able to do with that. Let's relate this to density now. Again, density, being a relationship between mass and volume, right? So if we think about N being substituted for M over molecular weight here, see if you can follow this conversion here. These two equations, I just swapped these two guys. That's just doing some basic algebra so that molecular weight comes over here and then volume goes in my denominator. So that's all I did is I just kind of switched those variables. Right now these two equations are exactly the same, but what I want to show you here is now I can have mass over volume. We know that mass over volume is equal to density. So like we saw in sort of our earlier slides here, where I want you to be able to look at and think about the relationships, whether they're inverse or direct, we can think about the same thing here with our manipulations here. We can say that density is going to be directly proportional to molar mass. So again, if we've got density right here, density and molar mass, if I want to maintain this equality and I'm going to be increasing density, here's density, I'm going to have to increase my molar mass in order to have that same equality. On the other hand, it's inversely proportional to temperature. Because we are multiplying these two pieces together in order to maintain our equality, if one of these goes up, the other one has to go down to maintain that equality. So those kind of skills are going to be really important just from a qualitative standpoint, being able to think about, should this parameter be increasing or decreasing? We're going to have a lot of those logic checks that we need to think about. So the last little piece to this skill is related but not. It's thinking about how we measure concentrations of gases, and we measure concentrations of gases through something called partial pressure. So when we think about partial pressure, the amount of pressure that each gas molecule is going to contribute to the total has to do with how many of them there are there. For example, if we have a gas, a collection of gas that's say 75% nitrogen and 25% oxygen, well, those nitrogen gas particles are going to contribute more to the overall pressure than we'll have for the oxygen, only because there's more of it. So there's two equations that I want you to know. They'll be provided for you, but you need to know how and when to use them. The first says that the total pressure is really the sum of all our individual partial pressures. So for that example that we just went through, if the total pressure might be 1 atmosphere, and we had 75% nitrogen gas and 25% oxygen gas, then the partial pressure would be 0.75 atmospheres for our nitrogen and 0.25 atmospheres for our oxygen. You'll notice here that it's independent of whatever the identity of that gas is. So that's one equation. The sum of all of the partial pressures will equal the total. The second piece is thinking about just using this from a fractional standpoint. If we want to think about, for example, how much the partial pressure of that nitrogen gas would be, we can think about its mole fraction. So this is a new term to think about. We can define, remember, anytime you have fraction, I want you to think part over whole. So usually we draw this with kind of like a scripty X here. So the mole fraction of A is going to be the number of moles of A over the moles total. So this is going to be something that runs between 0 and 1, and you can sort of think of it like being a percent. So in our example with our 75% nitrogen and 25% oxygen, we would say that the mole fraction of nitrogen is 0.75. If we multiply 0.75 by what the total pressure was, and we said, let's say that the total pressure was 1 atmosphere, the partial pressure of nitrogen is going to be 0.75. So these two equations are sort of related to one another, and you will be given both of them, and there's going to be different times where it will make sense to use one over the other. But sometimes these equations are going to allow us to get at a piece of information that we might need to solve a problem, whether it's the total pressure of all gases or using one of these to then take the pressure that's given, the total pressure, and use it to solve for the partial pressure of our unknown. And we're going to see that play out with this equation on our next example here. This is going to be something that you will do in lab class, but it's actually going to be something that we'll have problems in lecture here that we'll work on. It has to do with collecting a gas over water. I'm going to run through the experiment here just because it's interesting, and maybe then it'll be a review when you do it in lab class. But the idea is if we are going to collect a gas over water, what that means is there's actually going to be water molecules as gas mixed in with our whatever molecule that we're looking at as a gas. So again, here we can see here's water molecules, and then here's the gas that we're interested in looking at. So let me just run through this experiment. Just again, it'll help you hopefully in lab when you have to do this. Let's imagine we're doing an experiment where we have a solid that we're going to heat here. When we heat that solid, we're going to drive off some gas. That gas is going to then come out, and it's going to be collected in this tube. So imagine we started with this tube sort of inverted and completely full of water. Well, what's going to happen is as this gas bubbles in here, it's going to push some of the water out as that tube fills with gas. Imagine if you were to kind of just go underwater and kind of blow some bubbles into something. It would force out the water that was there, and you'd collect that gas that you breathed out. Well, what's going to happen is because we're collecting this gas over water, what's going to happen is we're going to have a mixture of gas. And so what we're going to have is the total pressure is going to be equal to the pressure of that orange gas plus the pressure of water. Now with this experiment, we're going to want to figure out some parameters for our gas. We're going to want to know what's the pressure of gas that we generate from this experiment, because that's going to give us, in some ways, the concentration of it. So what we're going to need to do is find a way of measuring the atmospheric pressure that we're going to have. That has to do with what's down here. I'm not going to get into the weeds and the details of that, but this is one of those partial pressure kinds of situations, because if we know the total pressure, and you can look up on a table a constant for what the vapor pressure of water is going to be at a certain temperature, you can use that to solve for the pressure of just your gas. So this is just an example of a time that we're going to, in lecture, see a time when we'll use this equation. And again, you're going to have an opportunity to do that in lab as well. So that's kind of manipulating PV equals nRT, thinking about density, thinking about molecular weight, and then how we think about measuring concentration of gases using partial pressures.